Hello everybody, this is Dr. Christopher White, and in this lecture we're going to be keeping things relatively light. We're just going to be dealing with the formation of the universe. Now, before we get started on that, we're just going to take a second to have a look at a couple of key ideas in science, or in geology more accurately, that will come across on a relatively regular basis. Now, the first one is of course the term theory. Now, you, like me, have probably used the term theory very loosely in the past and normally incorrectly. Typically, when we say that someone has a theory, what we're saying is that someone actually has a hypothesis, essentially an educated guess. However, what a theory actually is it's an explanation for some observed phenomenon supported by a body of facts which have been repeatedly confirmed through observation and experiment. So a theory is essentially a scientific idea which has been proven as rigorously as is, possible in science. So from a scientific point of view, it's about as solid as you can get. Now the other topic down the bottom there is uniformitarianism. Now this one is, a geologic term more in general. So uniformitarianism, is the doctrine that geological processes that occur today, now that's throughout the entire universe, happened in the same manner and at the same rate in the past. So it simply says, if it's happening today, it happened in the past. Rivers have always flown downhill, they've always transported sediment in the same way, mountain rivers have always been rather fast flowing, meandering rivers on floodplains have always been rather slow flowing, etc, etc, etc. So that means in geology, what we can do is we can apply the modern world to the past, and so that allows us to essentially draw comparisons, and it also allows us to get our heads around what was actually going on. And uniformitarianism is a pretty solid idea. However, every once in a while it doesn't quite work, and we will actually be touching on that at a couple of points during the course. Alright, so let's think about the Big Bang. So, the Big Bang theory says nothing about what banged, why it banged, and what happened before it banged. And so that's a relatively important thing that we need to think about. So what was going on before the Big Bang? We don't really know. It's also a point that should be made, we should also make the point that when we talk about the Big Bang, what we're actually thinking about is some kind of epic explosion. In reality, it probably wasn't. In reality, it was probably just a very gentle expansion. So the term Big Bang may be a little bit incorrect. So alright, so we're going to start off around 13.8 billion years ago, and at that point we're going to form a singularity. So a singularity is a point in which the normal laws of space and time do not apply. Okay, so we're going to form this singularity. So after about 10 to the minus 37 seconds, so really soon after this singularity formed, it began to expand. It began to inflate. And what happens is inside this singularity, energy is being converted into solid matter, so the stuff that we can touch, the stuff that we're made of, and other fun stuff like dark energy, and of course the dark matter, which you've probably heard about, which we are currently trying to understand. So anyway, we're going to worry about the solid stuff, the stuff that we're made from. So in terms of the solid stuff, the universe was very quickly filled with exotic subatomic particles. These are things like gluons and quarks and bosons, and of course electrons. Now, gluons, quarks and bosons, you may not have come across them, but they're very important when it comes to actually building atoms. Okay, because they are the things from which protons and neutrons are constructed. So after about 10 to the minus 6 seconds, these exotic particles actually began to form another group of particles called baryons. And baryons include things like protons and neutrons. So after about 10 to the minus 6 seconds, what we have is we have a universe where we have gluons, quarks, bosons, electrons, protons, neutrons, all flying around super, super quickly. The universe is super, super hot. And I should say, by the way, these particles are moving around at speeds, really extraordinarily fast. We're talking, close to the speed of light in some cases. So after about, and this is a bit of a broad range, I apologise for this, after about 10 seconds to 20 minutes after the Big Bang, we're going to start seeing protons and neutrons begin to combine to form atomic nuclei, okay? So if you remember, in an atom you have the nucleus in the middle, and the electrons orbit around the nucleus, okay? If you remember, the nucleus of an atom consists of protons and neutrons, whilst the electrons orbit around them. Okay, so after about 10 seconds to 20 minutes, we're going to have the first atomic nuclei forming. Now, important point, when we're talking about atomic nuclei, we are not talking about fully formed atoms. Remember, an atom is a nucleus with the electrons orbiting around the outside. What we're talking about here is just the nucleus, no electrons. Now, this process is called nucleosynthesis. And nucleosynthesis is very, very important because it's going to start producing the first elements. And so what nucleosynthesis does at this point is it creates about 92% hydrogen. Now, I should point out these are hydrogen nuclei. And a hydrogen nuclei is simply one proton floating around by itself. So not exactly a particularly tough build. Now, there will also be a small amount of something called deuterium, which is an isotope of hydrogen, and that's going to consist of one proton and one neutron. So it has the atomic mass of 2. All right. Now, deuterium, remember it's going to come up later. We create about 8% helium. So helium nuclei consists of 2 protons and 2 neutrons, so atomic mass of 4. Remember, once again, the electrons at this point are not there. And we're also going to form a very, very small amount of lithium. Lithium is 3 protons, 1, 2, 3, and 3 neutrons, 1, 2, 3. Atomic mass of 6. Now, it's going to take around 300,000 to 400,000 years after the Big Bang for things to start slowing down. Okay, so all of a sudden, all these particles in the universe are going to start slowing down just a little. And they slow down just enough at this point to allow these nuclei to actually catch their electrons. So after about 300,000 to 400,000 years, we actually have proper atoms. So we have atoms that have a nucleus in the middle and electrons orbiting around that nucleus. So it takes around 500,000 years to actually get to the point where we have atoms. So geologically speaking, actually very, very quick. Okay, so that was the basics. So the next question is, well, how do we actually know there was a Big Bang? Which is a pretty important question. I mean, I'm just telling you that. What evidence do I have to actually support it? And the first thing is to remember, as scientists, we always need to admit we cannot be 100% certain that what we're actually, suggesting is 100% correct. We could be wrong. We have to always admit that problem. So there are 2 main pieces of evidence to support the Big Bang. Number 1, the universe is expanding. And number 2, we see the signature of the energy released by the Big Bang in something which is referred to as the cosmic microwave background. Alright, so expanding. So between 1922 and 1923, a chap called Edwin Hubble, you may know that surname, there's a giant telescope floating in space named after him, observed that galaxies, which were once considered to actually be part of our Milky Way, were actually very distant. So can you imagine a situation in the past, up until about 1920, everyone thought that when they looked through a telescope and they were seeing all of this stuff in the night sky, it was actually part of just our Milky Way, and that was pretty much it. So what he noticed was that the distance between these objects that he was observing and us was increasing over the 1 to 2 year period that he was making these observations. Okay, and he noticed that when he looked at things in things like galaxies as we now know they were actually moving away from us in all directions. So that's very, very important. So that's telling us that there's movement in every axis. Now, how did he actually come to this conclusion that things were actually moving away from us? So he did it by using what are referred to as standard candles. So a standard candle is an astronomical object of a known brightness. So think about it this way. If you're standing in the middle of a field in the night, and in the middle of the field you put a 60-watt light bulb, okay? Now you're standing right next to that light. Obviously it's quite bright, and you know how bright that light is. So you can take a light meter and you can measure how bright that light is when you're standing right next door to it. So you know the brightness at that point. Now what you're then going to do is you're going to walk, half a mile away from that light. Well, when you look back towards the field, what are you going to see? Well, you're going to see a tiny little pinprick of light, and it's going to be rather faint. So the further you get away from that light source, the smaller it looks and the dimmer it looks. Now the great thing is that the decrease in the luminosity, the brightness of that object as you get further away from it is actually a consistent thing. So you can essentially you can measure and you can therefore extrapolate how the luminosity changes the further and further you get away from that object. So therefore, as long as you know how bright the object would be if you were standing right next door to it, and you can measure how bright the object is when you measure it, when you actually see it through your telescope, for instance, well then, because you know the luminosity changes in a set way, you can therefore work out what the distance is. So it's a very, very simple idea, and these standard candles are extremely helpful. So Hubble used something which are referred to as Seafeed variables. Now, to be clear, I'm sure there are some people that are probably jumping up and down at the moment at my pronunciation of Seafeed. I found several different pronunciations of it on the internet, so you'll have to just live with the one I've gone for. So Hubble used these Seafeed variables, but there are other standard candles like type 1a supernovas. And just to give you some idea, here's a galaxy and here's a type 1a supernova down here. So this is a star that's exploding. And you can actually see this one type A supernova is actually exploding with a brightness similar to the core of this galaxy, which contains hundreds of millions of stars. So that gives you some idea about just how powerful this supernova is. But anyway, these standard candles are rather helpful to us because we know how bright they are, and we know how this brightness will change as we get further and further away from them. So as long as we can measure the brightness when we're looking at them through our telescope, and we know how that brightness changes with distance, we can very, very quickly work out what the distance between us and the object is. So it's all super straightforward. And so what Hubble did with this data is used it to prove that several galaxies were not actually nebulae as they had been predicted to be, but they were in fact distant galaxies in their own right, and they were actually outside our own Milky Way. All right, so, well, that's great, but it's not actually proving that things are expanding. Because obviously, as we just pointed out, it's proven that these things are quite a long way from us. They're not part of our Milky Way, but it doesn't definitively prove that things are actually moving away from us. So how do we actually get to that point? Okay, well, every element has absorption lines. Now, you might actually have seen something like this when you did high school chemistry, high school physics. Okay, and you'll know that if you pass light through an element, so in this case hydrogen, what's going to happen is the light that passes through that hydrogen is going to interact with the hydrogen, and it's going to produce these dark lines in the spectra. Okay, and in the case of hydrogen, the classic lines are these four lines right here. Okay, so we know the wavelength of light at which these 4 lines will occur. Okay, so now let's have a look at the sun. So as you can see, the sun has quite a lot of these absorption lines because, of course, there's lots of different elements in the sun. There's not only hydrogen, there's obviously helium, there's a bit of lithium, then there's some fun stuff like iron, calcium, carbon, oxygen, nitrogen, etc. So there's going to be lots and lots of these absorption lines. Okay, so anyway, so can we find the lines there, 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 and there? So yes, they're there. Brilliant. And they're also at the wavelengths where we would expect them to be. So everything is perfectly okay. We find the lines for hydrogen. They're exactly where they should be. Great. I should point out, by the way, you might have noticed there's obviously not a one-to-one correlation between these two diagrams. Obviously, as you can see, the spectrum behind is slightly different. I mean, for instance, you can see the green field here is massive. On this one, it's tiny. You know, same with the blue field here, much smaller blue field here, much larger purple field here. So, you know, the spectrum behind is different, and also the length of the spectrum is also different. I mean, all this dark stuff here and here is not really included on this diagram. So they're not going to, you know, line up perfectly. But anyway, moral of the story is if we look at our sun and we get the spectrum of light from our sun, what we see is we see the lines in that spectrum for hydrogen, and they're exactly where they should be on the spectrum. So what happens when we look at the absorption lines for things that are further away from us? So when astronomers like Hubble began looking at the absorption lines in the light from distant galaxies and stars, they noticed that something was actually a little bit wrong. So instead of the absorption lines being in the correct location, they actually noticed that they had shifted to the right. So the position of them had changed. So if we look at this, this is an absorption spectrum for the sun. Now, please bear in mind this is a very, very generalized one. Okay, what you'll see is the sun will look something like this, whereas a distant galaxy will look something like this. You'll notice the absorption lines are obviously shifting to the right, which is the red end of the spectrum. Okay, so what's going on there? Well, the first thing we need to remember is that light is a wave. And therefore, because it's a wave, light is going to have a wavelength. So that's the distance between two peaks in the light wave. Okay? So in terms of visible light, light that has a big wavelength is going to be towards the red end of the spectrum. Light with a smaller wavelength is going to be towards the blue-purple end of the spectrum. Okay? So the smaller wavelength, the closer it is towards the left end of the spectrum. The larger the wavelength, the closer it's going to be towards the right end of the spectrum. So what's happening is that the light is being what's referred to as redshifted. So this is caused by the distance between the light source and the observer, you and me, getting larger. So what's happened is that this star, in this case, has, let the light go. The light is flying towards Earth, but because the distance between the source and the observer is increasing, the light wave gets stretched as that distance increases. As the light wave is getting stretched, it increases the wavelength, and it causes the light to move towards the right end of the spectrum, the red end. And so what that also means is that the absorption lines will also go along and they will move to the right. So I hope that makes sense. So as the distance increases, the light wave gets stretched, the distance between the peaks increases, so the wavelength gets larger. That makes the light wave move towards the red end of the spectrum. And it also means the absorption lines will move towards the red end of the spectrum. So, as we discussed, that causes the light wave to become larger, and that has three effects. So the first effect it's going to have is that you won't see the original colour. So a lot of light being released is, from stars is typically somewhere in a kind of, yellowish kind of tint. And so what's going to happen is that yellow light is going to be stretched and it's going to become orange. And in the case of when it's really, really stretched over very, very big distances, it's going to become red. So if the distance is really, really, really increased, your yellow light steadily becomes orange and then eventually becomes red. This is why the term redshift is used. Obviously that produces a shift of the absorption lines towards the right, as we were just discussing. And it also proves the universe is expanding, because this object is moving away from us, and we can tell it's moving away from us because the light is being redshifted. We can see it, and we can also see the absorption lines that show it as well. So that is how we know the universe is expanding, by using the redshift of objects. So just to give you some idea, this is a picture called the Hubble Ultra Deep Fields. This is when they took the Hubble telescope and they pointed it at a very small area of the night sky, and they pointed it there and left it there for a very, very extended period so it could collect all the light it possibly could. And within this image, what you can see if you look very, very carefully is that there are little red splodges in these squares. And if you zoom in on them, here they are. These are all very, very small, very, very early galaxies. Now these galaxies, obviously, when the light left them, they would look something like this, kind of, whitish yellow to a kind of more yellowy kind of color. Okay, but because the distance between us and them has been increasing over time, those light waves that left the galaxy looking like this have become stretched, and they've moved from the yellow portion of the spectrum into the red portion of the visible spectrum, and so they look very, very red to us. Okay, this is probably a good point to take a break, so get up, have a walk around, go and get a glass of water, have a cup of tea, cup of coffee, whatever you like, and then come back in 5 minutes once you've had a bit of a break.